Hello and welcome to this video lesson on rate concentration graphs. It has specification reference 3.1.9.2 and our lesson objective for rate concentration graphs is we want to work out how to use rate concentration graphs to deduce the order with respect to a reactant. So the first thing, let's just make sure we know what we're doing. Rate concentration graphs. Let's remember what we did before. Before we did concentration time graphs. We didn't do rate graphs. We worked out the rate from the concentration time graphs by taking the tangent, and that gave us the rate. Now we're going to actually plot all those different rates against the concentrations and see what those graphs tell us about the order of a particular reactant. Okay, let's look at the next slide to help us with that. Okay, let's start off with a graph that looks like this. As you can see, it is a concentration time graph. And let's say, for example, our concentration changed with time like so. So as time progressed, the concentration of this reactant X decreased linearly like that. That's what our data gave us. And then what we could do is we could look at this particular concentration. Let's call that concentration X1 and take a tangent. In fact, it's a straight line, so it's going to be the same for all points, but we can get the tangent, and that might give us a rate of 3 moles per dm cubed per second. All right, and then this point, let's call that x2, it's a straight line, so that's also going to be 3, and that point, let's call those x3 and x4, so that they are both also going to be 3. And so then, and this is rate. All right, so we've taken our tangents, and they've given us an example, a rate of 3. In this case, it'd be -3, but we don't really worry about the negative number here. The rate is 3 moles per dm cubed. I'm short of space, so forgive me for not writing the units in. And then we're just going to plot those rates against the concentrations. So you would then take your axes like this. You can see this is now rate against concentration. So if we were going to plot x1, now x1 is actually this one here. That's x1, and that has a rate of 3, and x2 is here, x3 is there, x2 and x1 is there, and they're all 3. So we would plot the rate here, the rate here, the rate here, and all of them are 3. So then we would plot our line of best fit. I meant to do that in red. So we plot our line of best fit there, and that's what we would get. And if we got a rate concentration graph like that, that would tell us that this reaction was a zero order reaction. So for zero order reactions, they are the graphs that we get, whether they be concentration time graphs on the left or rate concentration graphs on the right. If they are shaped like this, then we call them zero order with respect to X, the reactant X. And intuitively, what you can see is that as you change the concentration of X, the rate stays the same. So any change in X has no effect on the rate, and that's why it's a zero order. Okay, so you have to just remember the shapes of those two curves for the two graphs, and remember that those shapes mean a zero order reaction, or at least a zero order with respect to the reactant X. Okay, so let's look at a different situation. Again, we've got here a concentration time graph, and in this case we do our experiment. That might be a continuous monitoring experiment, and we get some gas given off, for example. We turn the gas given off to concentrations of X, and this time we get a curve, and I'll draw this curve in blue this time. We get a curve that looks like that for this reaction. And then we take that and we get our rates again. So we might put our tangents here on these points, take our tangents, and then read the rates. So if this one is concentration X1, this one is concentration X2, if this one is concentration X3 and X4, let's write them up here, X1, X2, X3 and X4. The tangent for X1 gives us might give us a rate of 4. The tangent has slightly decreased its slope for X2, so that might be 3, and the slope has decreased further, so the rate is 2, the tangent and rate are 2, and for X4 it might be 1. So let's say we got those rates from our 4 tangents. Then we would take those points and plot them on a similar rate concentration graph. And again, let's put X4 here, X3, X2 and X1. So X4 was 4, let's plot that up there. X3 was 3, and that's 2, that's 1. Okay, so we've plotted them. So let's just, for completeness, let's just mark off our values here. So there are our rates. Then we plot our line of best fit, doing this in blue. So you get a straight line going through the points as our line of best fit. And what you can deduce from this rate concentration graph is that if you double the concentration of reactant X, then you double the rate. So there's a linear relationship between concentration and rate, a proportional relationship rather. And if that is the case, then you call this a first order reaction. It's a first order reaction, and for first order reactions, they are the shapes of our curves that we need to remember. So a decreasing curve for our concentration time graph, but a straight line, increasing straight line for our rate concentration graph. And that indicates first order with respect to X. And lastly, let's look at the third situation, which might look like this, like that. And so in the same way, we do our experiment, find our volume given off, convert that into concentration, plot our concentration time graph, and then when we've got our concentration time graph, we're going to take our tangents. So let's take this tangent, this tangent, this tangent, and this tangent. Alright, so we take our little tangents, right, and then plot our rates. So this rate might be 16, this rate might be 9, this rate might be 4, and the shallowest one after the most amount of time might be 1. So then we're going to plot that on a rate concentration graph again. So we plot those numbers and you get a curve that does look like this. So if we plot the points in the same order that we took the tangents, so you might have this point 16 up there, 9, let's draw 9 So you might have those points there where this was your 16, this is your 9, that was your 4, and that was your 1. And then we draw in our curve, which is an exponentially increasing rate. So this intuitively says that as you double the rate, then you're going to as you double the concentration, you're going to square the rate. So it's an exponentially increasing rate as you increase the concentration of your reactant X. And if that is the case, then this is a second order. That's a second order. The X is second order in the rate equation. Okay, so that is all you need to know about rate concentration graphs and how you use the shape of those rate concentration graphs to figure out whether for that reactant, in this case X, whether that is zero order, first order or second order. And in fact, there's nothing in reality to say that a reactant can't be third order, for example, but that's not in your spec. In your A-level spec, you deal with reactants that go up to second order. So if you had a reactant that was actually order 3, you would actually get a similar shape to a second order reaction, but that's outside the scope of your spec. And so if you see this exponentially increasing rate concentration curve, then you know it's a second order reactant. So lastly, let's just check our learning objective. How do we use rate concentration graphs to deduce the order with respect to a reactant? Well, let's use our memory. So zero order is going to be it's going to be like that for your concentration time graph, and it's going to be like that for your rate concentration graph. First order is going to be like that for your concentration time graph, and like that straight line for your rate concentration graph. And second order is going to be also like that, but like that for your rate concentration chart there. So this would be, these ones are your concentration time graphs, and these ones here are your rate concentration graphs. There, so hopefully that's been clear, and let me know if not in class.